Hello, grade 11s. In today's lesson, we're going to be looking at stoichiometry, and we are specifically dealing with questions that relate to percentage purity. So without any further ado, let's just have a look at this question. So it says iron is recovered from iron ore, which we are given the chemical formula, in a blast furnace. The following reaction takes place. So we have iron ore reacting with carbon monoxide to give us iron and carbon dioxide, right? They say in one such reaction, 160 grams of impure iron ore was reacted and 63 dm cube of carbon dioxide was produced at what? At STP, right? So this is what you should do whenever you are reading the statement. Highlight the most important information, because that will help you in terms of your calculation, right? So 6.1 says write down the definition of the mole. So how do we define that one? We say 1 mole of a substance is the amount of substance having the same number of particles as there are atoms in 12 grams of carbon-12. So 6.2 says calculate the number of carbon dioxide molecules that formed at STP, right? So we must calculate what? The number of carbon dioxide molecules. Note that it is not saying calculate the number of moles. It is saying the number of carbon dioxide molecules. So we know that the formula to calculate number of molecules is this one, where you say a number of moles is equals to number of molecules over Na, which is the Avogadro's constant. But then you can see that there is one thing that is that will stop us from calculating the number of molecules here, is the fact that we don't have the number of moles, right? So which is why this is 4 marks. Remember, if this was just a question whereby you needed to substitute so to choose the correct formula, substitute and get the answer, then this would probably be 2 marks or 3 marks. But then now this is 4 marks, which is telling you that you might need to use 2 formulas in order to get to the correct answer. So now let's look at what we are given here. We are given 63 dm cube of carbon dioxide. This is what we are given on carbon dioxide that we are trying to calculate here. And then we are also told that this carbon dioxide is produced at STP. Whenever we see this STP, we know that this rings a bell to us that we must use the formula that goes N is equals to V over Vm, right? And then in using this formula, this is where we'll get the number of moles. From getting the number of moles here, we can then use this formula to get the number of molecules. So you get the system of thinking that you should have when answering these 4 marks or 5 mark questions. So now starting with N is equals to V over Vm, we have our volume there is 63 as given, then over 22.4, we know this is the molar gas volume constant, and then calculating this one, we'll have 2.8125 mole, right? Then from this one, we can now calculate the number of molecules. So here I'm avoiding rounding off to 2 decimal places because it is not the final answer, so I do not want to be losing those digits. So 2.8125 is equals to N over the Avogadro's constant is always 6.02 times 10 to the exponent of 23. It is a constant, meaning it is always like that. Then you cross multiply here, your number of molecules will give us 1.69 times 10 to the exponent of 24. Then you just write molecules, right? So in that way you could have got your 4 marks. So probably here they would give you 2 marks, and then also here substitution and the correct answer. Then we have 6.3. It says calculate the maximum number of moles of iron that will be formed in the above reaction, right? So you will remember that in my previous video, the one that I did on stoichiometric calculation, I said that once you have the number of moles of one of the substances or one of the compounds in the chemical reaction, then it enables you to just use stoichiometric ratios in order to find the number of moles of the other required substance or or compound, right? So remember, in the previous question 6.2, we already calculated the number of moles for carbon dioxide. It's 2.8125 mole, right? Then this question 6.3 is asking us to calculate the maximum number of moles of ion, right? Of what? Of ion. So which one is ion? Ion is this one, right? So we must calculate the number of moles of ion. But then how will we be able to calculate the number of moles? We already have the number of moles of this one. That means we can now use the stoichiometric ratios in order to find the number of moles of ion. So what are we going to do in answering that question? We'll say, let's compare the ratio of ion to carbon dioxide. So the ratio, we get it from what? The coefficient. So this will indicate to us our ratios. So that means, what is the coefficient of Fe, ion? It's 2. The coefficient of carbon dioxide is 3. So the ratio is 2 is to 3. But remember, we already have the number of moles for this one. So it's that. Now we are looking for the number of moles of ion. So we put X here. Then it's just a matter of cross multiplying here. And then 2 multiplied by 2.8125. Then to calculate X, we'll have to divide both sides by 3, and then X is equal to 1.875 mole. So just like that, we have calculated the number of moles of ion. So consequently, you can do that with any other compound that is in here. Let's say you wanted to find the number of moles of carbon monoxide. Since the ratios are the same here, you would then deduce that the number of moles of carbon dioxide and carbon monoxide is the same. And then you can also use that one to find actually the number of moles of iron ore, which is what we're going to look at here. 6.4, it says calculate the percentage purity of the iron ore sample used. Okay, so now to calculate the percentage purity, it says in one such reaction, 160 grams of impure iron ore was reacted. The percentage purity formula goes as percentage purity is equals to the mass of the pure substance over the mass of the impure substance, and then multiply that by 100, right? So this is the formula that we will be using here. Then from here, you can see that we are given the mass of the impure. That means before we use this formula, we will have to get the mass of the pure. The mass of the pure is the same as the mass that will react in here. Remember, the impure sample will not all react, because remember, we are trying to only to extract out the iron from this. So remember, the iron ore has some impurities, right, which we will need to get rid of. So in that case, we can say that the iron ore cannot all react. So now we need to find the iron ore that actually reacted, which is the pure iron ore, right? So to calculate that one, we will say, now let's first use the ratio. So we have iron ore to what? To carbon dioxide. Remember, we calculated the number of moles of carbon dioxide. That means everything will now be compared to this carbon dioxide. So the ratio is 1:3. So the number of moles is 2.8125. Then here it's X. Then to calculate the number of moles of iron ore, cross multiply here and there. So it's 2.8125, and then we divide both sides by 3, and then our X is equal to 0.9375 mole. Again, I'm avoiding to round off to 2 decimal places. It is not the final answer, right? So now that we have this, what can we do? We can now calculate the mass. Remember, this is the number of moles. So if we have the number of moles, we can calculate the mass of what? Of the iron ore. So here we are trying to calculate the mass of the iron ore. So the number of moles, we substitute 0.9375, and then it's equals to the mass over the molar mass. The molar mass of the whole iron ore is 160 grams per mole, and then cross multiply here, the mass will be 150 gram, right? So now to calculate percentage purity, again we say percentage purity is equal to the mass of the pure sample over the mass of the impure sample, and then multiply that by 100. Right. So what is the mass of the pure? We calculated that from the impure iron ore, only 150 gram of the was pure, right? And then 160 represents the whole iron ore, which is impure. Then we multiply that by 100. So our solution will now be 93.75%. Awesome. Okay, so we have question 5. It says potassium chlorate is a strong oxidizing agent that has a wide range of uses. It can be a component of explosive, fireworks, safety matches, and disinfectants. In a school laboratory, it is used to generate oxygen in the following balanced reaction. So we are given this balanced reaction here. And then it says 2 samples of potassium chlorate with equal mass of which one is pure and one is impure are placed in open containers on a balancing scale as shown in the diagram below. So we can see that this is a balancing scale giving us a mass of 130 gram. So we are told that the pure sample and impure sample have the same mass, which we can see from the initial masses. And then we can see that their final masses are obviously different. Then 5.1 says explain why the mass of the flask with its content decreases. So the solution to that one is simple. It lies on the statement. They told us that this is placed in open containers, right? So if this is an open container, it tells us that this is an open system whereby the gas is allowed to escape from the reaction vessel. So we can say this is an open system. The oxygen gas is able to escape from the reaction vessel. Then 5.2.2, it says 5.2.1, it says calculate the mass of potassium chloride that will form from the impure sample, right? So we have this impure sample, it's 130 gram, but then as we stated in 5.1 that the oxygen gas will escape from the reaction vessel, it means that the masses here, the final masses, are actually representing the masses of the potassium chloride, as we know that all the oxygen will escape from the reaction vessel, and what will be left will be this solid, right, which is potassium chloride. So that means in answering 5.2.1 we can just say the mass is 60.79 gram, because remember they told us from the impure sample, right? And then 5.2.2 says calculate the mass of the oxygen gas that will form from the impure sample of potassium chlorate, right? So remember we already have the mass that will be formed of potassium chloride from the impure sample, which is 60.79 gram, right? So now using this one, we know that consulting our stoichiometric calculations, we know that we will have to find the number of moles of potassium chloride, then compare it to the oxygen gas to find the number of moles of oxygen gas, and therefore calculate the mass of the oxygen gas that reacted. So to rewind down on the steps, you will remember that we said step number 1 here is to obviously calculate the number of moles of potassium chloride. So if you haven't watched that video on stoichiometric calculation, make sure you watch it. I will drop the link below. So N is equals to M over big M. And then what is our mass here? Our mass we're given to be 60.79, and then divide that by the molar mass of potassium chloride, which is 74.5. So if we calculate this, we will have a number of moles of 0.816 mole, right? And then from here we can just use this one to find the number of moles of oxygen gas. So step number 2 is to use ratio coefficients. So use ratio coefficients, and then now we say what is the ratio of potassium chloride to oxygen gas? So from here we can see that the ratio here, the coefficient of potassium chloride is 2 and the coefficient of oxygen gas is 3. So the ratio is 2 is to 3. Then obviously we have to put our 0.816 just below potassium chloride because it is for potassium chloride, and then X here. So to calculate for the number of moles of oxygen gas, it's 2x, cross multiply this 0.816, multiply by 3, and then divide by 2 eventually, and then X is 1.224 mole, right? Then we know step number 3 would be to calculate for the required value. So step number 3, calculate mass of oxygen gas, right? So this is N is equals to M over big M. So we have 1.224 is equals to M over the molar mass is 32. So if we cross multiply here, our mass is, let's calculate. So we have 1.224 times 32, that gives us 39.17. Rounded off to 2 decimal places. So it's 39.17 gram. Okay, then we have 5.2.3, which says calculate the percentage purity of the impure sample of potassium chlorate. Then you will remember that we said that with stoichiometric calculation, once you have the number of moles of one of the substances here, you can just from there on use the ratios to find the number of moles of the other substance. So we calculated the number of moles of this one to be 0.816. Now to calculate the number of moles of potassium chlorate, we would have to just compare the masses here, and then thereafter we calculate the mass. So it's potassium chlorate to potassium chloride, then it's 2 is to 2. So if we have the same coefficient, that means we also have the same number of moles, right? So the ratio is the same and therefore the number of moles is the same. Then 0.816. So what do we do to calculate the mass? Again, it's this formula, N is equals to small m over big M, and then here we substitute our 0.816 and then calculate the mass. The molar mass of potassium chlorate is now 122.5. So we are putting the molar mass of this one because we are looking for the mass of that one. Then cross multiply here, it's M, and then we have 0.816 multiplied by 122.5. This gives us 99.96. So we have 99.96 gram. And then to calculate the percentage purity, we know our formula is percentage purity is equals to mass of pure over the mass of impure, and then multiply that by 100. So the mass of the pure is the one that we just calculated now. So it's 99.896 over the mass of the impure is the one that we were given as the initial mass, and then multiply that by 100. So we have 99.96 over 130 times 100. That will give us a 74.89%. Nice. 6.2, it says the balanced equation for the reaction of sodium chloride, which is NaCl, with sulfuric acid H2SO4 is as follows. So we are given that chemical equation there, and it is balanced, right? Then during a reaction, they say 1.5 gram of an impure sample of sodium chloride reacts with 100 centimeter cube sulfuric acid of concentration 0.1 mole per dm cube at room temperature, right? Then 6.1 says define the term concentration. So for 2 marks, let's run quickly to that. We say concentration is the amount of solid per unit volume of a substance, right? And then 6.2.2 says calculate the number of moles of sulfuric acid used in the reaction above. So now for that, let's look at the data that we are given here. It says during a reaction, 1.5 gram of an impure sample of sodium chloride, so this is on sodium chloride, reacts with 100 centimeter cube of sulfuric acid. So this is the first information we are given on sulfuric acid, and also a concentration of 0.1 mole per dm cube. So now looking at our data, we can say that we are given the volume of the sulfuric acid H2SO4, which is 100 centimeter cube. But then we know this is not in the desired SI unit. So what must we do? We must divide this by 1000. So we have 0.1 dm cube, right? So this is the first thing that you want to do, guys, when you are faced with these questions. You want to collect your data. Then we are also given the concentration of sulfuric acid, which is 0.1 mole per dm cube. Now having this, we can see that to calculate here the number of moles, we need a certain formula. But then how do we get to choose the correct formula? It's by the collecting of data here. So now that we have volume and concentration, we know the formula to use here is the one that goes C is equals to N over V. Then obviously we have our concentration as 0.1, and then number of moles here, and then we have our volume again as 0.1. So if we cross multiply here, we have 0.01 mole, right? And just easy peasy like that, you have your 3 marks. Then they say on completion of the reaction, it is found that 460 centimeter cube of hydrochloric gas has formed. Then 6.2.3 says calculate the percentage purity of sodium chloride. Use 24.45. So use 24.45 dm cube as the molar gas volume at room temperature. So you can see here that we are given the molar gas volume is 24.45. That means they do not want you to use the 22.4, which is standard temperature and pressure, right? So in this case, you're still going to use the same formula, because Vm only appears in this formula. So Vm only appears in the formula V over Vm, but then instead of substituting 22.4, now you're going to substitute the one that you are given there. So you always have to note these questions and make sure that you read your statements correctly. So now let's start. We are given the volume here for this formula. We are given the volume is 460 centimeter cube, and this is the volume of what? It's the volume of hydrochloric acid. So what must we do? Divide it by 1000. So it's 460 divided by 1000, and then this will give us 0.46 dm cube, right? So this is our volume in the desired SI unit. Now from this you can see that we are given the volume of hydrochloric acid, but then we are asked to calculate the percentage purity of sodium chloride, right? Of sodium chloride. So if you still remember the steps that we went through with a stoichiometric calculation, is that I told you that they will not give you what you are looking for specifically, but then they will give you another compound here or another substance that you will need to find the number of moles from, and then use your coefficient ratios to find the number of moles of the one that you're looking for, and then thereafter calculate the mass and then calculate your percentage purity. So let's first start by the formula for percentage purity, so we understand what is going on. So the formula for percentage purity goes as mass of the pure sample. So it's mass of pure sample over the mass of impure sample, and then you have to multiply that by 100, right? So now that means we are given the mass of the impure, as when reading here it is given that 1.5. so we were given here that 1.5 gram of an impure sample of sodium chloride reacts with 100 centimeter cube. So this 1.5 gram, we won't be using it. We'll only use it when it comes to this formula. So the first thing that we have to do with that question is to first calculate. So step number 1 is to calculate the number of moles. So calculate a number of moles of the hydrochloric acid. Remember, we've been given the volume of hydrochloric acid And this hydrochloric acid forms at room temperature. So that means we can use this formula. So the volume, remember, it was 0.46, that 460 centimeter cube, then over Vm is 24.45 as given on the question. Divide that, we get that our solution is equals to 0.01881. So let's just round off to at least those decimal places. And then now that we have the number of moles, what can we do? Let's compare the ratio. Let's compare the ratio of sodium chloride to the ratio of hydrochloric acid, right? So we find that the ratio there, according to our coefficients, is 2:2. So as we can see here, the coefficient of sodium is 2, and the coefficient of sodium chloride is 2, and the coefficient of hydrochloric acid is also 2, right? Then when we have that ratio, what does it mean? If we have the same number, that means if this one has a number of moles of 0.01181, this also is 0.01881, right? So same number of moles. Then what do we do from here on? We must calculate the mass. We must calculate the mass of the sodium chloride. So we have 0.01881 is equals to mass. And then when we calculate there, we have 58.5, right? So when we cross multiply here, our mass is equals to 1.1 gram, right? So to calculate percentage purity, again, remember the formula is what? Mass of pure sample over the mass of impure sample. So what we were calculating here is the one that reacted, which is the pure sample, and then over the impure sample, and then multiply that by 100, right? So we find that our percentage is equals to 73.33%, right? Awesome.